Plate tectonics is a scientific theory that describes the large-scale motions of Earth's lithosphere. The model builds on the concepts of the continental drift developed during the first decades of the 20th century. It was accepted by the geoscientific community after the concepts of seafloor spreading were developed in the late 1950s.
The lithosphere is broken up into tectonic plates. On Earth, there are 7 or 8 major plates, depending on how they are defined, and many minor plates. Where the plates meet, the relative motion determines the type of boundary: convergent, divergent, or transform. Earthquakes, volcanic activity, mountain building, and the oceanic trench formation occur along these plate boundaries. The lateral relative movement of the plates typically varies from 0 to 100 millimeters annually.
Tectonic plates are composed of ocean lithosphere and thicker continental lithosphere, each topped by its own kind of crust. Along convergent boundaries, subduction carries plates into the mantle. The material lost and roughly balanced by the formation of new oceanic crust along divergent margins by seafloor spreading. In this way, the total surface of the globe remains the same. This prediction of plate tectonics is also referred to as the conveyor belt principle. Earlier theories that still have some supporters proposed gradual shrinking, contraction, or gradual expansion of the globe.
The outer layers of the Earth are divided into the lithosphere and the thermosphere. This is based on differences in mechanical properties and in the method for the transfer of heat. Mechanically, the lithosphere is cooler and more rigid, while the asthenosphere is hotter and flows more easily. In terms of heat transfer, the lithosphere loses heat by conduction.
Tectonic lithospheric plates consist of lithospheric mantle overlain by either or both of 2 types of crystal material. Oceanic crust, in older texts, it's called sima, from silicon and magnesium, and continental crust, which is called sial, from silicon and aluminum. Average oceanic thickness is typically 100 kilometers or 62 miles. Its thickness is a function of its age. As time passes, it conductively cools and becomes thicker. Because of its form at mid-ocean ridges and spreads outwards, its thickness is therefore a function of distance from the mid-ocean ridge where it was formed. For a typical distance, oceanic lithosphere must travel before being subducted. The thickness varies from about 6 kilometers or 4 miles thick at mid-ocean ridges to greater than 100 kilometers or 62 miles at subduction zones. For shorter or longer distances, the subduction zone, and therefore also the mean, thickness becomes smaller or larger respectively. Continental lithosphere is typically 200 kilometers thick, though this also varies considerably between basins, mountain ranges, and stable cratonic interiors or continents. The 2 types of crust also differ in thickness, with continental crust being considerably thicker than oceanic